Thank you for joining us for today's webinar, Beat the Heat, a coatings response to climate change. We have some brief housekeeping here before we start. Your phones are muted, and if you have any questions, please type them into the Q&A box in the corner of your screen, and we'll answer them at the end of today's session, time permitting, or via an email after. And you can always send questions to mapeidigital@mapei.com. And we also invite you to visit our website, www.mapei.us, and visit our Concrete Restoration Systems page to check out our Elasticolor line of products, which are managed by today's speaker. Without further delay, I'd like to introduce him, Rankin Jays. Rankin is the Business Development Manager, Coatings, for MAPEI's Concrete Restoration Systems line. He's spent virtually his entire career in the paints and coatings industry, with a great deal of international experience across all facets of the business. During his career in the United States, he's been responsible for channel sales, marketing, and product management for several regional and national brands. He has a business development leader. He's been, a business development leader with MAPEI Corporation since 2015. And he holds a BS in psychology and an MBA from universities in New Zealand. I also always enjoy his webinars because he's a really funny speaker. But today's going to be especially interesting because it focuses on a topic that we've all seen all the time in the news, and it's very hot right now, if you'll excuse the pun. With that, I'm going to welcome him to the microphone. Rankin, the floor is yours.
Hey, good afternoon, Jen. Thanks very much. Appreciate it. So yeah, we're glad to be back with you, Jen, and the listeners there. I hope everybody's having a good day and an enjoyable week. So yeah, we've got Beat the Heat here, and what we can do is a simple application of some coatings to make life a little bit more comfortable for everybody. So in this presentation, we're going to talk about the sort of within the scope of climate change discussion. We're going to talk a little bit about heat islands, how they've been caused, and how they impact us. We can then understand the importance of increasing thermal emittance and solar reflection of the buildings we erect, and how with that, how we can, with a simple coatings application, result in a reduction of energy consumption. You'll already have an awareness of the various cool roof code standards, some of the programs out there, but I'm going to introduce you today also to a relatively new initiative for cool walls. I apologize ahead of time if I'm going to get too heavily involved in the physics side of this discussion, but I don't want you to leave here today thinking that I've got some magic beans that I want you to buy from me. So I am going to spend a little bit of time on the physics. So wherever we are in the climate change debate, I think it's undisputable that the global weather patterns are changing. Air and sea temperatures are rising. Ice caps and glaciers are retreating. CO2 concentrations have increased. And weather events are becoming, extreme weather events are becoming more frequent and more intense. And these physical manifestations are quite obvious and very, very easily measurable. At the same time, our global population topped 8 billion in late 2022. And although growth rates have slowed and they will continue to slow in the developed world, it's obvious that the demand on finite and non-renewable resources of the planet is going to continue globally. Without significant intervention, continued amplification of these climate change events seems inevitable to me. And that a solution is going to be the work over several generations and right across the globe. You know, it took a long time to get here, and it's going to take a long time to put it right again. But with the growing population and rising prosperity, particularly in the developing countries where this demand growth will be the greatest, doesn't necessarily affect us here in the States, does it? However, from a global standpoint, it's going to be a very significant and sustained draw on resources. I'm saying that, you know, things aren't going to get better globally. Certainly here in the US they will, but it's going to be in developing countries, they're going to be contributing more to the problem than solving it. So moving forward, we'll have less to do with the problem, but we'll have a bigger part to play in the solution. So the US was one of the first countries to industrialize, starting in the 1870s, and by the 1920s, it made the switch from a predominantly rural population to an urban one. You know, with urban centers initially developing around transportation hubs, it's estimated that 3% of the Earth's surface is occupied by urban centers. And while it doesn't sound like much, consider the fact that only 10% of the Earth's surface is actually habitable. So, you know, there is a lot of space covered by cities and urban areas out there. And today, more than 80% of the US population lives in urban centers. Urban areas are characterized by large expanses of sealed surfaces, dark impervious materials, roofs, walls, parking spaces, roads, and a notable lack of green space. Tall buildings form urban canyons that block air movement. Waste heat from vehicles and AC units also exacerbate the problem. Rainfall's channeled away in storm water, meaning there's less cooling by evaporation, and of course, because of lack of vegetation, there's less transpiration as well. By contrast, a rural setting, there's less heat absorption to start with, and that we have a natural cooling effect from groundwater evaporation and transpiration from the vegetation. You know, in urban areas, our preferred construction materials are concrete and steel, which act like a heat sink, absorbing and holding energy throughout the day, only to start releasing it again after sundown. The EPA estimate that the daytime temperatures in urban areas are between 1 and 7 degrees Fahrenheit higher than an adjacent rural area on the same day. Nighttime temperatures 2.5 degrees hotter. 2 to 5 degrees hotter. Whilst everyone is affected to some degree, it disproportionately affects marginalized groups and inner city communities. And it's not a new phenomenon either, though. Scientists first noticed the heat island effect occurring in the early 19th century, but it's obviously got a lot worse as our climate changes, urban population increases, as well as the size and density of our urban areas increase in mass. This is an interesting quote from Christina Dahl. You know, she's a leading climate scientist, and she said that in an average year, in the US, heat kills more people than any other type of extreme weather. You know, the statement is a statistical interpretation of available data, but somewhere in the order of 1,300 deaths in the US every year are directly attributed to extreme heat. Inhabitants of urban areas are obviously more vulnerable to these elevated temperatures. You know, at the same time, there are also a number of indirect outflows from the urban heat islands, increased demand on the electricity grid, resulting in potential brownouts, reduction in air quality, the development of smog, and the stress on infrastructure and social services as well. We understand what the heat island is and recognize that that with a changing climate, there's not going to be any better without some intervention. And it's a vicious cycle. As the climate gets more extreme, the more energy we expend to individually combat the effects. It won't even matter if we've managed to attain a carbon-free electricity production by 2035 or be net zero by 2050. You know, I made the point earlier that climate change is a slow process and we'll have little control on what's happening on the other side of the planet. Heat events and urban heat islands are going to be around for a while. So that's where we can look at some of our architectural materials to provide us with some immediate short-term relief. The concept of using white and light color finishes on exposed building surfaces to control heat is not new. In some areas of the world, it's been the way of life for the lack of infrastructure or the availability and affordability of air conditioning. But it wasn't until the late 1990s in the US that we started to pay some attention to the science behind the energy saving opportunities. In 1998, a bit of a timeline here, you know, takes us back to 1998 when the US Green Building Council launched the LEED program, and that drew focus on the building supply chain, how products are made, their efficiency, and how they're brought to market. The Cool Roof Rating Council was established in 1998 to develop fair and accurate and credible methods for evaluating and labeling service radiative properties of roofing products. And that's specifically solar reflectance and thermal emittance of roofing products. That was quickly followed by an update to ASHRAE 90.1 in 1999. That has long been the benchmark for commercial energy building codes in the US. Cool roofs quickly became the fastest growing sector of the building industry, and with California adopting Title 24 to their building energy efficiency standards in 2001, really saw this movement accelerate. And today, this is the scope of the codes and ordinances and standards that are in effect. In each case, there are specific solar reflectance and thermal emittance criteria, but at the cornerstone of each of these standards is the measurement standard proposed by the Cool Roof Rating Council and has been adopted as the standardized test measures. These apply to all roofing materials, whether they're roll, sheets, fluid applied, and you can be sure there are individual requirements and exclusions within each of the standards depending on where and what materials are being used. Having said that, the discussion of these is beyond the scope of this presentation, but to draw a quick example from the 2022 California Title 24, this is one of the prescribed requirements. There are individual requirements for occupancy type, low slope roofs, steep slope roofs, and potentially different requirements depending on which California climate zone you're in. Note that they're required to have a minimum aged solar reflectance and thermal emittance of these values. I emphasize the word aged because when the roof is first constructed, everything is new, bright, and clean. But then on exposure and over time, there is weathering which degrades the surface and provides the potential for buildup of dirt, grime, organic material, etc. that will reduce the solar reflectance and thermal emittance values. The standard testing prescribed by the Cool Roof Rating Council is an initial measurement performed by a laboratory. Samples are then put on a 3-year test fence, and after that time, they're measured again to give us the aged measurements. The manufacturer then updates their credentials, or if they don't meet that age minimum, they're removed from the accredited list. Obviously, that can be problematic for a manufacturer trying to bring products to market today, but doesn't qualify under the test specification for another 3 years. Fortunately, Cool Roof Rating Council Cool Roof Rating Council have developed an aging calculation for roofing materials to avoid such an issue, allowing roofing materials to enter the market with a provisional approval. And if my math's correct, we'd need an initial solar reflectance of about 0.9 to calculate an aged solar reflectance of 0.63 after 3 years. Thereby, it meets the Title 24 standard. And that's not a reach for most products, well, certainly white-colored roofing products. So what are solar reflectance and thermal emittance? Solar reflectance is the measure of the amount of solar energy that's reflected by the surface, of the energy absorbed by the structure. Some of that will be transferred through to the interior space. The balance will be released again to the environment through emission of radiation. The efficiency of the material to release energy is thermal emittance. Both of these measures are on a scale of 0 to 1, or you can use a percentage if you like, 0 to 100%. The higher the number, the more efficient the material is. So going back to Title 24 for a moment, we also see an acceptance criteria for products that have a solar reflective index, an SRI of 75. So here's another variable that we're adding to the conversation. Once again, this is on a scale of 0 to 100, but it's a calculated measure, complicated series of steps and factors that factors in both solar reflectance and thermal emittance to arrive at an index number. So why is that important? Well, on an aged system, it's theoretically possible for a product to lose the solar reflectance over time, but it will maintain a high level of thermal emittance, and it could still qualify on the basis of the solar reflectance index. So I hope I haven't confused you with that, but there are many online calculators for this purpose, and using various combinations of thermal emittance and solar reflectance, you can see this relationship at work. Solar reflectance can be easily improved by utilizing lighter colors that are more reflective. And it doesn't get better than a high contrast white, for example. Snow, in fact, freshly fallen snow actually does have the highest reflectance value of all. Well, I should segue here with a comment, and hence our concern about the ice caps, right? Okay, I'll move on. And we can also influence this by using certain types of pigments in our coatings as well. And we'll come back to that shortly too. Thermal emittance is influenced more by the nature of the material and properties of the surface being measured and less to do with color, although a study did determine that green colored products, as in color green, have a higher emissivity than and may be linked to why chlorophyll is green. Nonetheless, concrete has a better thermal emittance than steel. Textured concrete is even better again, and I can only assume that's because of the larger surface area that becomes exposed with the texture on the surface. And similarly, common red bricks have a better thermal emittance when they've not been fired or glazed. So it sort of puts you in a, gives you a handle on some of what we're talking about in terms of building materials for facades. But for the most part, we associate heat with visible light. And in this case, the sun accounts for about 45% of the sun's radiation. The visible light is accounted for by 45% of the sun's radiation. And as you see in the diagram, it's within a very narrow wavelength band. And it's these wavelengths that also give us our color association. A further 54% of the sun's heat reaches us in the near IR wavelength bands. And while it's invisible, it imparts a great deal of heat energy and is largely responsible for the heat island effect. So we can put that into context with this illustration where I'm measuring the surface temperature, not thermal emittance or solar reflectance, but just the surface temperature of each of these sample boards. They're the same type of cement board substrate with the same exposure to the sun on the same day, and the photos were taken within seconds of each other. And they've all received the exact same amount of near IR radiation, but the difference in temperature comes from the absorption of the energy in the visible light spectrum. So while that's a very narrow wavelength band, they are shorter wavelengths and capable of generating almost as much heat energy as a near IR. So what we're talking about is the accumulation of near IR radiation plus the visible light radiation, depending on what color it is. So you can see, quite a temperature swing there between the white and the black, and then just the generic cream color in the middle there. And so turning our discussion to cool walls. Exterior walls receive about half as much sunlight as roofs, but typically have about half as much insulation. It's much easier to insulate a flat attic space to the depth of 10 or 12 inches with insulation, but harder doing that in a vertical wall because of its dimension and construction materials. There's limited space between the studs in the wood frame construction, and access to wall cavities in brick and CMU construction is nearly impossible. A city is comprised of high-rise buildings that will have substantially more wall area than roof area. Therefore, dark walls can heat buildings and contribute to an urban heat island effect just as much as a dark roof. So is the solution to the heat island effect that we all live in white houses with low slope white roofs? Well, ideally, yeah. The titanium dioxide that colors our paints and coatings has a very high solar reflectance. It reflects all the visible light spectrum and a large portion of the near IR wavelengths as well. You know, it'd also make our lives as paint manufacturers much easier if you all just buy white paint. But of course, we know that won't happen because we all do enjoy our freedom of choice and personal expression. So while the relative lightness and darkness of color is an indicator of solar reflectance, it's not an absolute. We can also incorporate some underutilized pigment technology to enhance certain color ranges to improve solar reflectance. You know, through the selection of special chemical compounds like mixed metal oxides or titanium dioxide, it's possible to achieve a much higher total solar reflectance, especially in the near IR spectrum. The solar reflectance of light and medium tone paints, for example, can be greatly improved with the addition of IR reflective pigment, hence the term cool colors. The improvement of solar reflectance is even greater when we start phasing towards the darker shades, including black. And you'd be surprised how many paint colors, even in the pastel and medium shades that we've got on our houses, incorporate a little bit of black. And that's enough to really shift the scale in terms of solar reflectance. But going back to these images, if we were to have used the appropriate near IR reflective pigments in the beige and the black finishes, we would have raised much of the temperature imparted by these samples by near IR radiation. The visible wavelengths would still have generated some heat, but the thermometer reading would be significantly lower. And then using a FLIR camera, this image demonstrates just that, and the benefits of painting a facade with a cool wall coating. The left side of the building is painted with a regular pigmented house paint. The right side has been painted in the exact same color, except it's been pigmented using IR reflective pigments. So then viewed in through a forward-looking infrared camera, we see the resultant solar reflectance of the infrared temperature of the surface, and you can see that the effect the white door has, for example, but also the cooler wall that's been coated with the near IR pigment product versus the regular coating. And I'm kind of interested in this image also because you can also see that thermal transfer of the studs as well at various temperatures. So anyway, an interesting example of what we can actually achieve. So the IR reflective pigments color space is not as complete as other paint tint systems, but with a very small amount of compromise, it would be possible to get you a high performance cool wall color that generates immediate savings on your utility bill. And of course, do something good for the urban heat island effect. But I should point out that these are not commonly available and will not be available in your favorite hardware or paint store. The technology is still very selectively utilized in the paint industry, and but that's not to say it's not being used in other areas of roofing and siding products. About 10 years ago, I was actually involved in developing and launching a cool wall coatings line at another employer. At that time, there was only one other manufacturer using this technology or trying to launch it as well. Unfortunately, the program appeared to be ahead of its time. Distribution partners saw little need, and there was not the government or utility company incentives that were associated with cool roofs. Neither was there the support from lobby groups like USGBC or Cool Roof Rating Council. So yeah, sadly that folded and took with it some inventory, but never mind. What goes around comes around. And it was also not like, we didn't have sufficient data either, but both Lawrence Berkeley National Laboratory and Oak Ridge National Laboratory host what they call a heat island group. And that's a bunch of PhD scientists. And they, in 2005, they performed a joint study with the Department of Energy and also Oak Ridge, setting up residential test sites around the country, one in Phoenix, one in Jacksonville, Florida, and one right there at Oak Ridge in Tennessee. And accordingly, they were able to develop a cooling model. And these were all for testing an IR reflective cool wall coating. And they were able to develop a cooling model by construction type and location and calculate annual cooling energy savings of between 4 and 22% on your energy utility bill. Savings were found in all climates, having in excess of 1,500 cooling degree days using a 65-degree baseline. The higher percentage of savings were actually for CMU walls, with typically have a lower R value. So hello, I live right here in Florida with in a building constructed of CMU, and pay quite a lot on my electricity bill. So at this point, I'm actually reminded of the Bruce Willis line in Armageddon, and to politely paraphrase him, it's this is the U.S. government, and I'm sure you have teams of people sitting around just thinking stuff up. Yeah, they do. And these guys at Berkeley and Oak Ridge, have done a very thorough job on a lot of this analysis and investigation into urban heat islands. The Cool Roof also heavily involved with the Cool Roof Rating Council, to make a point as well. The Cool Roof Rating Council actually coordinated the formation of a wall rating program committee. I think it was at the beginning of 2021. And that was from a cross-section of industry partners to develop the guidelines for the Cool Wall Rating Program. And as of January 2022, they began offering product ratings for companies interested in having their exterior wall products listed and labeled with product radiative performance. It follows closely on from the Cool Roof Rating Council Cool Roof Rating Program. Exterior wall products are independently tested for initial solar reflectance and thermal emittance. Manufacturers are given an initial approval to the list of their products as a cool wall product, subject to the results of a 3-year aged exposure. And once again, the product must fall within a defined criteria specified by the program owner or the local body. So this obviously doesn't compare to the list we have for cool roofs, but they took 20 some years to get to that level. But it's off to a good start here with Hawaii Building Code providing an insulation concession if the wall surfaces have a solar reflectance of 0.63. That's pretty good considering the cost of construction and certainly the comparative cost of a coat of an IR reflective coating or a cool wall coating compared to additional insulation that you have to install in the walls. Actually 90.1 has a cool wall requirement for climate zone 0, but the latest version will offer an energy credit for climate zones 1 and above. Cal Green, that's a stretch code, only becoming mandatory if a local jurisdiction adopts it. But the cool wall movement was really given a boost by the Greenbelt, US Greenbelt Council with a pilot credit in LEED 4.1. The heat island mitigation credit is available if at least 75% of the building's exterior is covered with a cool wall material with initial solar reflectance of 0.6 and thermal emittance of 0.75. Numbers are, as I said earlier, they should be fairly easily achieved with light-colored coatings. So it is a pilot credit, but the hope is that that's going to just roll on over into the coming years as well, and help us drive this cool wall program. So hopefully we'll see some rapid growth with the cool wall rating program as a result of the collaboration by a large number of coatings and facade material manufacturers, and backed by the proven integrity of the Cool Wall Rating Council. You know, and you know, it's tough to get. Sorry. Okay. So I don't. Just in summary, I don't have an estimate for on the effect of cool walls or cool roofs that are expected. You know, the expected effect on an urban heat island, but the science all points to say it should. Other structures, other studies from the folks at Berkeley say that you know, 85% of all, if 85% of all air conditioning buildings in the US have white roofs, associated energy costs for buildings would be reduced by $735 million annually. And by increasing the solar reflectance just by 1% across that 3% of the planet that's occupied by urban areas, we would reduce CO2 emissions by 44 gigatons. And I have no idea what that means, but it is the equivalent to the CO2 emitted by 300 million vehicles. And that's about as many vehicles we've got on the road here in the United States. And remember though, it's a one-time deal. It doesn't actually recur every year thereafter. It's a one-time savings on CO2 emissions, but it would actually set the path to correcting our CO2 emissions. These past 2 summers, we've also seen cities across the country recoating roads to reduce temperatures and also help trying to mitigate the heat island effect. You see the one top left there, that's Arizona, California, and you can see the advantages of doing that with a FLIR camera image. You know, and we know that the same physics has to apply to cool walls. This is another opportunity to provide commerce and industry with some low-cost measures to positively impact lives, the climate, as well as their profit and loss statement by saving themselves some energy cost. The same opportunities exist for us as homeowners by investing in cool color materials for our next re-roof or repaint. You know, the technology exists and the opportunity, and now what remains is just a question of buy-in and execution. So, you know, with that, I will finish, and really do appreciate your attendance today. And I think we do have a little bit of time available for Q&A, if that's okay, Jen. Jen? Okay.
Hi, can you hear me now?
I can hear you now.
Hi. Oh boy, I'm talking away. Sorry about
I thought I'd been talking to myself for 30 minutes.
Nope. It was unmuted, but it was muted at the source here. So sorry about that. I apologize.
No worries.
Rankin, for a very great presentation as always. And yes, we do have a few questions. So let's get started, shall we?
Sure.
The first question, are cool wall coatings just as good as regular paints? And do they cost more?
Oh, excellent. I was hoping it was going to be a physics question. I was worried it was something like that, but no, I love it. This is right in my wheelhouse. No, yeah, they are just as good. They use the same ingredients as a regular paint or coating. The only difference is the pigmentation that's used to produce that final color that you've chosen for your property. But in some ways, they could also be considered superior for the reason that they reduce the associated heat buildup in the wall, and thereby reduce the thermal cycling of expansion and contraction in the coating and the substrate. So, you know, the less the wall moves, the less likely it is to crack, the less likely you're going to have moisture mitigation issues, moisture issues or leaks. Okay, but oh, and the other part was as for the cost. The pigments are a little bit more expensive, but we're only adding 2 or 3% of the pigment by weight to a 55, 60 pound bucket of paint. So the incremental cost does not amount to much. And with a lot of technology, the more it's used, the cheaper it gets. So yeah, initially I can see that there'd be a small premium, but over time, as more folks buy into this cool wall coatings, yeah, that price will come down. And more users, more manufacturers, more competition. Competition usually drives price down.
Exactly. Yep. Great. Great question. All right. Oh, okay. Not quite physics, but numbers for you. What is the numeric relationship between solar reflectance and temperature?
Okay, I think I can see what we're trying to get at here, and this is very general. But
Yeah.
for a 1% improvement in solar reflectance, there's about a 3 degree to a 10 degree in drop in surface temperature, but there are several variables that play into that, like color and finish as well. So it's not an absolute, but and it really depends on the as I say, on the substrate we're talking about and the finish.
Yeah. Okay. All right. Give us some time. Here's one. You mentioned 1,500 cooling degree days in the cool wall study. Oh, someone was paying attention.
Yeah.
What is that? That's a good note. I thought I was taking notes. That's a good one.
Yeah. So cooling degree days are the difference between the average daily temperature at your location, the difference between that and a reference temperature. And I think I mentioned 65 degrees as being baseline. So if, let's take, for example, if your average daily temperature is 80 degrees and our baseline was 65, we have 15 cooling degrees for that day. So now we go through the year and we add up all of those 15, or whatever the number is, all those cooling degrees for the days, and we hit 1,500. The answer is you should buy a cool wall solution for the side of your property. So yeah, obviously here in Florida, that's a no-brainer. The further north you get, maybe we don't have 100 15-degree cooling days. So you know that number is going to come down. And actually, it also leads. And I don't want to drag this out too much longer, but it also makes a very good point that there are also heating penalties for having cool walls or cool roofs if you're too far north in latitude or you're in a cooler climate. That because of the thermal because of the solar reflectance and thermal emittance of these products, you're cooling in the wintertime when you don't actually really need it. So yeah, just a little aside there.
Oh, that's a very good point.
Mm-hmm.
Yeah, the opposite side of that coin.
Yeah.
Didn't even think about that. All right. Another question. How is solar reflectance measured?
I know that there is equipment there.
Yep.
Typically, it's a piece of equipment called a spectrophotometer or a reflectometer. They have those for all sorts of applications, but I believe there's a specific one for solar reflectance. Yeah, and I couldn't go into much more than that without revealing weaknesses in my knowledge. But, but
Right.
at the same token, solar reflectance, thermal emittance is also a measure we need to take. And I do know that they usually use a thermocouple or a resistance temperature detector that's actually adhered to the backside of the facade, um, or just underneath the surface of the facade material to capture that information.
And you can read it. Yep.
Mm-hmm.
It's very interesting, isn't it? I mean, you had that picture that looked, was it the FLIR camera
Yes. Yes.
reading? That's fascinating. We can see all the leaks.
Mhm. Oh, for sure. Yeah.
Yeah, yeah, yeah. Well, we'll
Is that
see.
it?
Are there any more? Yeah, I'm waiting to see if there's any more questions coming in. We'll give people just a minute more or two. I know if they're anything like me, as soon as the webinar ends, you think of, 3 more questions you wished you would have asked. And if that happens, you can always send your questions to Rankin directly, at his email, or you can send them to MAPEI Digital at mapei.com, and we will forward them on to Rankin, of course. And I know this will be recorded and posted, and I don't know when you'll be listening to it, but if you're listening to us live, Rankin will be at the World of Concrete coming up here next week. So that'll be great. You could speak with him in person. Um,
I look forward to that.
so
Thanks, Jen.
yeah, I look forward to it as well. Well, I guess that will bring this to a close. So I want to thank everybody for spending some time with us, and thank you, Rankin, very much for, again, another really great informative presentation.
My
And as I
pleasure.
said, thank you. I'm sorry, thank you. Thank you, everybody, for spending time with us. We know that you do have very busy days, and so the fact that you've taken some time to spend with us really does mean a lot to us. And again, if you do think of some questions, MAPEI Digital at mapei.com, and you can always visit our website, www.mapei.us, and we'll look forward to seeing you at the next webinar. Have a great rest of your afternoon. Bye.